Okay, so welcome to the second lecture in the introduction to Lattice Boltzmann in winter 25 and 26. So two small things about the last lecture. As I have already mentioned at the end of last time, but not in the recording, we had here forgotten to have the magnitudes in these velocities here. Yeah, so this was a mistake here. And then one of you pointed out later that we have used for the derivation of the ether theorem, we have used the collision operator as the time derivative of f. And of course, if you look in the Boltzmann transport equation, then of course we have, in addition to the collision operator, we have the force operator and we have the advection operator. So the forcing operator, as is common, the forcing term, yeah, the force term, as is very common in physics anywhere. When we have a force somewhere, I mean a force field that is not balanced, then this is usually because we are not looking at a closed system. Yeah, so we use gravity as a force because we do not want to include the entire Earth or other things. So usually, if you look at the entire universe, then all forces are obviously balanced, and because we have not specified our collision operator, we could also include this in the collision operator, even I mean the far-reaching forces does not mean that it's necessarily very close. So usually we don't have force fields in when we integrate over the entire universe. But we have binary forces, things that can also be described as a collision. So we are not considering this thing. And the other thing is we have the advection term. And the advection term, which we could now prove mathematically that this drops out, but the advection term, what the advection term does is that it moves this f's from one location in space to another location in space without changing the actual value of this, right? And since we integrate over the entire universe, there is no way that these particle distribution function can escape from the universe. Yeah. So of course you're right that we would have to write all this down and prove this, but it's actually common not to do this because this is these are two. I mean, the advection is something that obviously does not change the eta function, so we just ignore it in this. So okay, this far for last week. Now let me briefly change this here. Oh, Daniel, you will be on YouTube. Your face will be on YouTube. Do you mind?
No. I don't.
Okay, now it's gone. Not at all. Okay. Otherwise, I have to blur you. Okay, so let's come to the second part in the to the second lecture, where we talk about the equilibrium function. Of course, starting with what we had last time, the ether theorem. Yeah. So again, ether was this integral over f in ln. Okay. So it does not matter ln or log. Yeah. It's just a factor. So I'll now be lazy and write it like this. And the time derivative of eta, we have seen this is smaller or larger than 0. And the equilibrium is the case when this does no longer change, meaning that if this is 0, then we call this the equilibrium. So we call this the equilibrium, and then we had, as the reminder, what we had there, dt. So this was 1/4 of this integral over b f1 dash f2 dash, which we call the gain, minus f1 f2 before the collision, which we call the loss, into this logarithm of f1 f2 minus the logarithm of minus of f1 dash f2 dash, and all of this we integrate over xi1 xi2, the entire universe in all the directions. So, and we've seen that this here is smaller or equal to 0, and b is larger or equal to 0, yeah, because it's a probability of something happening. So now this dH by dt, now I've said again, h, eta, equal to 0 will only happen. So I mean, because whenever these things are not identical, yeah, they will be negative, yeah, and so since they will always be negative in each single point in space, they can only, if the integral is 0, then they must be 0 everywhere, always, right? So this means that this is only if for all the xi1, xi2, and the xi1 after collision and xi2 after collision, f1 after collision, f2 after collision minus f before collision, if this is 0. This is here a condition, and this this obviously means that the product of the two are equal. And again, this can be written in the way that the logarithm of f1 plus the logarithm of f2 is equal to the logarithm of f1 dash plus the logarithm of f2 dash. Yeah, so because it's the product of the two is the same, so the sum of the logarithms are also the same. So then there was a conjecture by Maxwell that he could write this equilibrium in terms of a Gaussian distribution that would only depend on these conserved quantities. So this conjecture was later proven by Boltzmann, I think I've written it here, 1872. We are not looking at the proof today. So the equilibrium depends only on the conserved quantities. And it's so annoying, this thing. which are of course the mass, momentum, and the energy. Mass, momentum, and energy. Okay. (72). Is this in the book? It should be in the book, right? Is it? I have not looked. I don't know how complicated this proof is. Okay, and maybe another year we do it. But we have so many things to learn that I don't want to spend too much time on kinetic theory actually. So the thing is like this: the logarithm of this. I mean, okay, we should say in equilibrium, yeah. In equilibrium. So, and the logarithm of the equilibrium can be written as a simple polynomial of a plus the constant part b times c. So this is a vector plus c, and here the square of the velocity, yeah? So where A, B, and C are the, well, constant is not the right word. I mean, the parameters of this equilibrium, yeah? So, and if we take now our left-hand side, left-hand side of this equation 2.1, then we have the logarithm of f1 plus the logarithm of f2, and this we can call as 2 times, okay, we add these two together, and this is supposed to be a parameter for the mass. Then we have B, scalar product of, what should I do? I think I have to buy such a, something, a glove, yeah. I mean, it was so simple in the previous Windows, it just turned this up here, but okay, sorry. So we add these two velocities together, and this is the combined momentum. And then we have here C, and here we have C1 times C1 plus C2 times C2, and all of this together is the energy. And if we take this in comparison to the right-hand side of equation 2.1, then of course here we have the post-collision state of both of them together, with again 2a, which is conserved, yeah, so this is the same, plus b, so the velocity after collision plus the velocity the second after collision. So also this is the same because it's conserved, and then we have plus the energies after collision together after collision. They are of course also the same. So, and this can then be more conveniently written in the FEQ is equal to E by the power of A E B times xi plus c xi dot xi. And of course, usually do not write e by the power of a, but we define this as a different constant, obviously, yeah, because this is that would be simply inconvenient to have it like this. But I mean, what you see is that this is Gaussian distribution, at least if c would be negative, yeah, so we did not exclude that this would be negative, that has a bias of b, right? So it's shifted by b, yeah? And it's with the variance being the energy. Okay, so suppose we accept that this is our equilibrium. What do we do with our equilibrium in order to solve this integral, the collision integral? Because we have this complicated collision integral, and we somehow want to deal with this in a usable way. And one way how this was done is the single relaxation time approximation. Or it is also called, after the, should say, inventors, the Bagnaga Cross and Krug, and this was done in 1954. So this actually has nothing particular to do with Lattice Boltzmann, because Lattice Boltzmann came only in 1985 or aroundish, yeah. So I'm actually older than Lattice Boltzmann. I guess you are much younger than Lattice Boltzmann. And so it's usually called BGK. So one of them is obviously an Indian, one of them was from South Africa, and one of them was from America. I think that Krug sounds South African, I believe. It was otherwise I don't know. So what is the idea? We know from this ether theorem that the collision will drive the distribution towards the equilibrium. Yeah, so we have a distribution that looks somehow and that goes into the collision, and we know that the one that goes out of the collision is closer to the equilibrium. Yeah? So what they thought is, what we can do is a linear interpolation between the incoming state and the equilibrium state, and we just vary the distance that we go along this linear interpolation. So this looks like this. So first let me write so the collision drives the distribution towards equilibrium. Okay, so the idea looks like this: df by dt. So just the collision, not the advection. So it was proposed to look like this. We have so the change will be related to F equilibrium minus F divided by tau. And this tau is called the relaxation time. and physically it is related to the mean free time between collisions. Did you read the sign?
No, we didn't.
Okay. Sorry for the. We have we have multiple occupations of this room. I had to throw them out. Okay, so what is the idea? The idea is, in principle, when two particles collide, they forget everything. They forget their history, and their history is in this distribution. So they come in as something, and they go out as equilibrium. Yeah, and the difference is now how long does it take that they go to equilibrium, and this is the time between collisions. Yeah. So every time they collide, they basically go locally in equilibrium, but they are not colliding continuously, but they have a time that they fly in between collisions. And this is the mean free time, and this is basically related to this relaxation parameter tau. Okay, so you're asking questions. Does that mean that the equilibrium is even then reached when other entities are still changing, as long as mass and momentum and energy are not changing? I don't know how. This is. I'm not reading you all the time. This is the question is referring to the definition. Equilibrium depends only on the conserved quantities, mass, momentum, and energy. Quantities, not entities. Okay, so that was a little bit too much. The question equilibrium, so does that mean that the equilibrium is even reached when other entities, quantities are still changing? Well, the equilibrium, what do you mean the equilibrium is reached? The equilibrium is reached at the end of the world, in a sense, right? So I guess I kind of misunderstood the question, as long as mass moment. Okay, so finally some interaction. Okay, we are talking about in this email, yeah, but please ask questions. It's just, these people here have the advantage of they can step in, and I don't look at the screen all the time because I have to look at the other screen. Please.
The relaxation time is like we are considering like one particle in one velocity state, and it collides. This is the time, and another after collision up till the equilibrium. So these two times we are considering.
So we are okay. We'll discuss this further in a forthcoming lecture. But we are actually looking at there is a particle that basically comes out of equilibrium, yeah, because it had a collision last time. So it had a collision, and then it will fly to another place where there's a different mass, a different velocity, and a different energy. Yeah. So once it moved, it is no longer in equilibrium unless we have no gradients in our system, right? So, but suppose we have gradients in our system, then it will move to a place where the same quantities are not the same. And then we have a combination of populations that have part. I mean, what we do is we take this Gaussian distribution, cut them all in pieces, and add them together with other Gaussian populations, which have different parameterization, and therefore, because they have different parameterization, they do not fit to each other. So if you cut out the one distribution with the other distribution and combine them, you have no longer a Gaussian distribution, right? So they are not in equilibrium. And this time is the time that the particle flies from its last collision to the next collision. Yeah. So, but don't worry, we'll discuss this again. Okay. So just here for the idea how this works for after collision. So say we can now integrate our distribution from t to delta t, and this would be the population that we had before, plus the integral from t to t plus delta t over this FEQ minus F divided by tau over dt. Now, when you integrate this, of course, you have to consider that FEQ is not constant, yeah, but it depends on the change in the conserved quantities, right? Okay, how are we doing this time? Not very good. So the conservation laws according to this collision operator, which it always hurts me a little bit because it's not mathematically, it's not really an operator, but we call it operator. Okay. Conservation laws. So obviously, this thing here, whether it's an operator or not, has to have the usual conservation laws. Yeah, so which means that the mass, which is the first one of this integral, you see, we have the distribution afterwards, and we have the distribution before, and they have the same mass, they have the same momentum. Yeah, so this means that this here is not allowed to change this, which means that FEQ minus F divided by tau. So this integrated over all velocities. Yeah, so we can exchange momentum between different velocities, but if we integrate over all the velocities, this needs to be 0. So it does not change the mass. Yeah, particles can go from one velocity to another velocity, but they are not created or destroyed. Yeah, so the same thing applies to the momentum. The same thing applies to the momentum, where we have, oops, this looks ugly, where we compute the momentum like this. We take the momentum of this operation here. We take this BGK thing and we multiply this with the velocity, with the microscopic velocity, and integrate it over the microscopic velocity. And this also needs to be 0 because it's not supposed to change the momentum. And the same thing is also supposed to be for the case for energy. And energy we get out of this by multiplying this with the square of the velocity and then do the integration. So they all need to be 0. And these things here we call the moments or the conserved moments in this case, of the BGK, so this is how we call the single relaxation time operator after the inventors, the moments of the BGK operator. I think I've used moments also last time, but so in this entire lecture, we'll always talk about moments, moments, moments. So what is a moment? A moment is an integral property. So something that you get out of an integral. Integral properties of distributions. I have no idea why they have been called moments. I think moment sounds like one moment in time, yeah, but okay, I don't know. So these moments are basically what we use to translate from the statistic over particles to the primitive variables that we have in continuum theory, like in the Navier-Stokes equation, where we have the density or the pressure and temperature and velocity. Yeah, so it's kind of this transformation. From, say, the statistical, which is this F, statistical to primitive. I also don't know why these variables are called primitive, but so primitive variable is velocity and pressure. They are primitive variables of the Navier-Stokes equation. If anybody can tell me what is primitive about them, sounds like an insult. Okay, now if you look potentially into some of the books, and in particular in the papers, you will find simplified. You'll often find a simplified definition of how we get to moments, and we come to this in a minute, but I actually want to briefly go through how we really get to these moments. So that requires a little bit of, well, I don't know, definitions. So let's this F of capital F of Xi, capital Xi, where I put this is a vector again. So this is the capital Xi. We'll come to what this means. So let this be the bidirectional Laplace transform of F of small xi. So you all know what Laplace transform is, or you have heard about the Laplace transform, but not everybody is completely happy all the time with the Laplace transform. Yeah, so you use the Laplace transform you go into frequency space, right? And then depending on whether you are a mathematician or you are electrical engineer, you call this variable either S or P, yeah? But the thing is, you're doing a transformation from a frequency, that's not the frequency space, from a spatial space or a temporal space, a temporal space to a frequency space, yeah? Where you replace then T by S, yeah? And what we do is we replace Xi which we call the direct space, if you will, and its frequency is this capital Xi. And we do this in 3 dimensions because we are in 3-dimensional velocity space. And unlike the usual Laplace transform, we do it for the positive and the negative half space, right? So you can also do the same thing just with the Laplace transform, where you just have, instead of this capital, you would have, instead of the capital Xi, you have the I times, what is this called? This is imaginary unit times the frequency, right? So it's basically the same things, just a little bit shorter to write this. So now we write this as like this. So we integrate, so I said bidirectional, so I go from -infinity to infinity in all directions over f of Xi, and I multiply this by e by the power of Xi dot frequency Xi, and I integrate over Xi. And now when you are careful, you already notice that there is something strange, because in the Laplace transform usually we have a minus here. Yeah? So, and for whatever reason I could not find out, our convention is the opposite here. I mean, this is like, this actually looks like the inverse transform, right? So because in the inverse transform you have a plus, in the forward transform you have a minus. The same thing with the Fourier transform, right? And for whatever reason, it is the other way around. If we don't do it this way, then all velocities in the universe are negative. And somehow negative defined. Okay, I could not find out why this is the case. Maybe somebody of you finds out and tell me. So the sign convention is opposite to usual, but this doesn't change anything with regard to the theory. So sign convention opposite to. I mean, this led to a lot of errors in my papers. So yeah, the frequency. Okay, I'll write the frequency like this. Again, we take this capital Xi as the first part. Then this here, this ugly thing, is supposed to be a big upsilon, and this here is supposed to be a big theta, okay? So this is what we are going to use. And now this f of Xi, this is called the moment generating function. The moment generating function. And the way this thing generates the moments is like this. So we can write the moments, and we give the moments 3 indices because we are in 3 dimensions, M, A, B, C. And now we take derivatives of this thing. So I say this is the 8th derivative. Sounds crazy. 8, not the 8. Yeah. So the A order derivative in this Xi. Yeah, and the B order derivative in this upsilon, and the C order derivative, we are running out of letters later, in theta on F, on the F, and we evaluate this at the position 0. So where should this be familiar to you? Gradient? Yeah, I mean, gradient is the first derivative, right? No, it's, I mean, especially because we say we evaluate this at a specific point. So where do we have some increasing derivatives that we evaluate at a specific point? Smiling. In a Taylor expansion. So obviously what you are doing here is you take this Laplace transform of f, yeah, and you generate the Taylor, the what is it called? The coefficients, right? The coefficients of the Taylor expansion is just what is missing is this 1 over factorial thing, right? So, but this is a constant. That doesn't matter, yeah. So this is the series expansion of this of the Laplace or the Fourier transform. By the way, the Fourier and the Laplace transform have some interesting properties, and one of the property is that if you take a Fourier transform or Laplace transform of a discrete function, you get a continuous function, right? And this is important here because if this was not a continuous function, then this derivatives didn't make any sense. On the other hand, you can think about it like this. We treat this f kind of as a continuous function. However, this is not necessary, and in principle, in nature, this is also not the case. Because there is there are discrete particles, after all, yeah? And this funny thing works even with discrete particles, because this f can be a discrete function. If we take the Laplace transform of this, we have a continuous function of which we can take derivatives. Yeah? And I think this is actually the place, so this is my interpretation, philosophical interpretation, but this is the place where we have the connection between, we have actually atoms, yeah, in nature, and still we can describe them as a continuous function, yeah, because we have this transformation in between. Okay. Okay, let's write this down so that we don't forget it. So it's the coefficients of a series expansion of this f of xi. So, because we are Taylor expansion needs a development point, and this development point is 0. Frequency zero means basically no gradients, right? So this entire thing gives way to a very strong simplification, as I indicated before. So in this simplification, again, I think I've mentioned this already, but we take this xi as xi, upsilon, and zeta, so this vector, yeah, and now we can take the entire complicated thing here, MABC, put the definition of, there's always a lot to write here, unfortunately. I'm not sure whether we can make this more efficient. So this is not a gamma, this is it looks like a gamma, the upsilon. DC zeta. So, okay, we plug the integral in here. Fc and Exc dot zeta. Okay, so and we evaluate this later at zeta is equal to 0, and then we integrate this over xi. So we notice that the only occurrence the only occurrence of theta is actually here. Yeah, so we can, and also that, why do I say theta? Xi. Also this xi here, the big xi does not depend on the little xi, so we can integrate this forward. What I mean, we can actually drag this into here, and what is then going to happen is, okay, we take the derivative of an exponential, yeah, so the derivative of an exponential will give us this, okay, the integral will stay here, f xi, so we get a very simple polynomial, because if we take a derivatives of this thing up here, yeah, we get 8 times, yeah, this xi out, and the same thing for upsilon, and then the same thing for theta, and this goes into e xi and times xi that we evaluate at xi equal to 0. So if we evaluate this to, so it does not appear anymore, so I can now put this xi equal to 0 here. So I have e by the power of 0, which is 1, and so I end up with an integral of this xi by the power of a, upsilon by the power of b, and theta by the power of c, and that's it. So what I often see in the papers, at least in Lattice Boltzmann literature, is that the definition of a moment starts from this. Yeah. So, and I mean, this is probably also the right way. Yeah. Because you get obviously you get to this simplification, but to know what you are doing, and actually to do a little bit more clever things, you should always know where this originally came from. Yeah. So this is only the outcome. This is not the definition. And sometimes we have to go back to the definition, yeah, to make some changes here. And this will be necessarily later. But here we have this kind of simplification. So this gives us the countable raw moments, as we call them. Whereby raw, we mean they are in the lab frame, or in the Euler frame, if you prefer this. So this means they are measured according to something that we define to be at rest. Euler frame. And okay, why are they countable? They are countable in A, B, C. So, but they are not countable. They are vector countable. Yeah. So you cannot count them in just one direction, but you have to count them in 3 directions. Yeah, you can count A, you can count B, and you can count C, but you have to count all of them separately. No, it was the same question. So that's not the only way that moments get defined. So there are other opinions. Why is this computer becoming loud? I mean, there's in the Lattice Boltzmann literature, there's a lot of opinions, I have to tell you. So other definitions So you can define moments in different ways. So for example, you can use a different frame of reference. So different definition of what you call velocity zero, right? Then you can include orthogonality conditions. This is something that we have a look on later today. And then there is normalizations. I mean, you can scale things just to a different scale. You can divide them by something, yeah? Okay, what about the frame of reference? So, suppose we start with our, no, wait. Let me write the Eulerian frame. The Eulerian frame is the laboratory frame. Where you have a bench and this bench is at rest, right? So, meaning there is a stationary observer who can decide that something has a certain velocity compared to the observer, right? So this gives us here, so if this is xi and this here would be xi equal to 0 in our lab frame, and this here is our distribution f, then this will in general not be centered, but we'll have a distribution that may look like this. And now we can center this around a velocity u and say we have a different I won't always say populations distribution that is shifted, where the coordinate, the frame of reference is shifted such that the thing is in the center. And this is what we then call the Lagrangian. The Lagrangian frame. So, and we can define this Lagrangian frame f or distribution as the one in the old frame shifted by this velocity. Yeah? Now this will now be a centered function. I do. So what does this mean for our transformation? If we go back to our Fourier transform and say now this is supposed to be the Fourier transform of the shifted distribution. Okay, so the reason why I struggle with population is because later in Lattice Boltzmann we call the individual the discretization of the distribution, we will call this populations. This is why I'm always struggling keeping this out, because this is only true for the Lattice Boltzmann method and not for the Boltzmann theory in itself. Okay, so we have this integral here, so we'll put this the f with the tittle, what is it, yeah, whatever, on it, This comes here with plus u, okay? Into e by the power of xi times xi, and this integrated over xi. So now, since you see that we go from minus infinity to infinity, and what you see we can do is we can shift the entire system by u, right? So that we can rewrite this. So it's still from infinity to minus infinity to infinity. So I'm not writing plus u. So, but we shift the entire integral such that we have only xi here, and we have, therefore, we have to also shift this xi up here in the opposite way, in the opposite direction. So we have xi minus u here, and this into xi and we integrate this over xi. And now we can do the same thing. We'll take the derivative according to xi, to the big xi, and then we get we get multiple times this thing here out, right? And this leads us to what we call the central moments, which we write now with k in order to distinguish them from the one that we call with m, k, a, b, c, where we have the integral from minus infinity to infinity, f, now of xi minus u, so u is the x component velocity, and this by the power of a. Yeah, so we replace xi by xi minus u completely, and upsilon minus v by the power of b, and theta minus w by the power of c, and this we integrate over xi again. So starting from, okay, I'll write here that this is again in the Eulerian frame, right? We write f, we still have f in the Eulerian frame, and then we get the centered moments out of this. So these are called then the central countable moments. So because they are centered, they have by definition they have their first moments. So their first moments are related. The first moment is a bias, right? So first moment of a centered distribution is always 0. Yeah, because this is how much it is not centered. Yeah. So basically you define u such that k100 is 0. Right? This is how you find what u is actually supposed to be. So of course this is the same thing in the other directions too. So these things that we call the first central moments are always 0. Instead, obviously, if A is equal to 0, B is equal to 0, and C is equal to 0, yeah, so you get them, then all the U, V, and W will disappear, and then you have this density moment or mass moment, and this is what we call Galilean invariant. This means it does not change if we go to a different frame of reference. So then M000 is equal to K000, called the zero moment. The zero moment is the same in the centered or not centered frame. So, I've already called these up here the first order moments and this here the zero order moments. So definition is that the order of a moment is the sum of its indices. There are two ways of writing indices correctly, and this is none of them. Indices, I don't know. So, for example, how many second order moments do we have? 6, right. So we have 6 second order moments. So all these permutations. So there's M200, M020, M002. So these are 3. And then we have the others, M110, M101, and M011. So these are the six second order moments. So the second order moments are, for example, so some of them, or a part of this tensor, if you will, is related to the temperature. So temperature in raw moments. Looks a bit complicated. Okay, so T is equal to M. So the M is the mass of the particle. So far we have just said there is a particle or there is no particle, but this particle has a mass. Right? And this divided by 3 rho. Okay, now I'm a bad guy. So this rho here is the particle density. It is 1 over cubic meter. Yeah? It says whether a particle is there or not, and not how much mass is there. Right? It may be a little bit inconsistent with all of this. K. Boltzmann. The 3 comes from 3 dimensions. The integral over f over xi, so this is the lab frame Eulerian distribution function, and here this is actually defined as the centered velocity. So these are now vectors, and there is a scalar product of the centered velocity with itself. Okay, this scalar product, this can of course now be expanded. Is a little bit annoying, but we do it anyway to see what this leads to. So we have xi dot xi minus 2u dot xi plus u dot u. So, and in order to be even more annoying, we write this out in its components from minus infinity to infinity. So again, f, I don't write f of xi now. So here we have, of course, xi square plus upsilon square plus zeta square minus 2 u xi minus 2 v upsilon minus 2, what is it, how we call it, w zeta plus u square plus v square plus w square, and this we integrate over xi. Okay, why am I annoying? I'm annoying because I wanted to point out that now these guys here, they depend on the variable we integrate over in the square. These here also, but these guys here do not. And actually, we can split the integral, as you see, with just f integrating over this, and then we get the moment m200. And we can also split this here, then we get m020. And here, because u is a constant as far as the integral goes, this will give us minus 2 u m 100, right? So we can write these things here down as m divided by 3 rho k Boltzmann. Yes, m200 plus m020 plus m002 minus 2u m100 minus 2v m010 minus 2w m001. And then, okay, so the others. So they also will give us a moment, but the moment they give us is the moment m000, because they go with all of this by the power of 0, right? So, and now we are going to identify what these things are. So we already said this here is the density moment. So this m000 we call rho, and this m100, now this is the momentum, but it's not the physical momentum because we have not the mass with it. So it's a particle momentum, if you like, yeah? It's the density of particles that you have, of the countable particles, times its velocity. So it's rho times u. And m010 is rho times v, and m001 is rho times w. I'm not losing anybody with this. No, it's clear. Okay. So then you see, when we plug this back in, then part of this will disappear because we have here 2u m100, which is also u, yeah, times rho, and this will partly disappear with this guy here, so that we end up with t being this prefactor m200 plus m020 plus m002 minus u times u into rho, which is, see, this is our actual thermal energy. So no, this is the total inner energy, and this is the kinetic energy, right? And if we write this in central moments, then it's pretty easy to do this. So you can derive it, but you could also say, okay, writing the same thing in centered moments, and since temperature is a Galilean invariant quantity, is a quantity that does not depend on the velocity of the stuff, yeah. So we can simply do the same derivation in the centered velocity frame, and in the centered velocity frame, u is 0, right? So that this means we can simply write without doing any calculations that this would be m divided by particle density and k Boltzmann into k0200 plus k020 plus k002. So this is the velocity in, sorry, the temperature in centered moments. Okay, let's have a look at some moments of the equilibrium function. So since this, I guess this is because it was Maxwell's idea and Boltzmann's proof, this thing is called Maxwell-Boltzmann. Maxwell-Boltzmann equilibrium. Which we derive with some, this A, B, and C, yeah, but this can actually be identified, so written in physical stuff, and the physical stuff that comes here is then rho divided by 2 pi k Boltzmann T divided by m, and this to the power of 3/2, this multiplied by E to the velocity squared, the microscopic velocity squared times the mass divided by 2 k Boltzmann T. So, yes, so this is of course a non-shifted, a centered, centered distribution function. And this is a very important property of the entire thing, can be factored into its components. So there's no vector here, so this is xi square m divided by 2 k Boltzmann T. So this is, you can call me childish that I write all of this down. Of course you know this, but this is an important property that always comes handy and should always be remembered. This is why we write it down. The equilibrium factors in its directions. Yeah. So calculating the moments, and I have to admit that for this thing I simply used Mathematica. So having the countable moments of this looks like this, 2 pi. This 2 pi is annoying, but this is somehow required. E minus xi. Okay, I'll skip this and just write it in this form. M2kb t, and then of course we multiply this by xi by the power of a, upsilon by the power of b, and theta by the power of c, and integrate this over the entire xi, so over the 3 dimensions. Okay, now I've just said I could have split this up, and I'm also now going to split this up to make a point. Also, I make the point of taking this part here in front. So I'll take this out, 2 pi kbt divided by 2/3. So now I integrate. So we've seen this here can be written in these 3 parts here, right? So what I'm now going to do is I'm taking this out and write this is E by the power of xi square by times m and kb t, and I integrate this over a, and we multiply this with xi by the power of a and integrate this over xi. So, and then I close this one bracket here and leave, okay, we don't need this bracket, but I write a bracket here. So, okay, I'm integrating this only over one dimension of xi, yeah, because the other guys do not depend on xi, they depend on upsilon and theta. So I can distribute this and integrate individual over these different directions. So I continue and write this is e by the power of minus now upsilon square m divided by 2kbt, and I integrate this over upsilon by the power of b and integrate this over upsilon, and I close the bracket, and then I also multiply this by the integral from minus infinity to infinity over e by now it's theta square m divided by 2k Boltzmann t theta by the power of c, and this integrated over theta. Okay. Now the reason why we are doing this is to see how we can simplify the calculation of our moments. And so this already looks like that we can, that for at least for the equilibrium, and this is only true for the equilibrium, we can actually split or factorize the calculation of the equilibrium moments, but there is something missing, and this one thing that is missing here is the normalization. So let's normalize this thing, normalization. And this is, we have MABC, we're talking about the equilibrium, and we normalize this by the zero order moment. So if we do this, we have an integral from minus infinity to infinity over the entire thing here again. So what I'm doing, I guess I have to write all of this again. Xa, the theta, the xi, sorry. And okay, I write all of these things again, and then I do the same thing for the denominator. I'm always confusing these things in English. Yeah, so I'm doing the same thing for M00. Yeah, but I split this up again, and I will also write this thing here, which is simply the same, kbt. The only thing is that I multiply with xi by the power of 0, which is obviously 1. Then I write this down here. And then, okay, sorry for all the writing. E by the power of minus upsilon squared by m2kbt, upsilon by the power of, it is b d upsilon divided by minus integral from minus infinity to infinity, e by minus upsilon square m2kbt without upsilon, and this integrated over very ugly upsilon, and this multiplied with the last one. I should have done this in 2D. This would be as good as doing it in 3D. So theta by c, d theta, and this integrated E minus zeta square m by 2 kb. Okay, it's getting uglier the later it gets in. Usually we have the lecture at 8 o'clock in the morning, that would be. So, now this is how it looks like. So the problem is that this here is not a complete moment, right? Yeah, it's only integrated over one direction. Now, but if we take one of them out, the thing that you will notice is what we can do is if we take this one, e by c square m divided by 2 kb t, now not zeta, xi, a d zeta, xi, sorry, I can never say what I write. E by minus c square m 2 k Boltzmann t dxc. So now this thing can be very simply expanded, so I can take the other two integrals around this guy, yeah, and also my e by the power of upsilon square plus zeta square into m divided by 2 kbt, and I multiply this with the thing that I've written here, this xi square m divided by 2k Boltzmann t, and this into xi a, and this we integrate over xi, now upsilon and zeta. Now, why I'm allowed to do this? I'm only allowed to do this if I integrate both, yeah, the denominator and the nominator over the same thing, obviously. Yeah. So then when I do the same integral down here, I mean the same addition to the integral down here, what you notice is that both of them have now become the complete moment, the complete three-dimensional integral for the moment, right? So, and here's just xi, d upsilon, and d zeta. So, both of them now give together MA00 equilibrium divided by M000. Now you can say this is obvious, yeah, but it's very important that we are sure that this is obvious, because what this now means for the equilibrium, if we take this into the other part, is that we can write MABC at the equilibrium. If we divide it by M000, can write this as the product of MA00 equilibrium divided by M000 times M0B0 of the equilibrium by M000 times M00C equilibrium divided by M000. Important is this factorization applies to equilibrium and not necessarily somewhere else. So all of this was here to show that we can simplify very much how we compute the equilibria in higher dimensions, yeah, because they simply factorize. Okay, so there is one last thing, and since we have officially a 3-hour lecture, I'll take the liberty of taking some more time than the 2 hours now, even though we have not an exercise today. The orthogonality. So this is a very, in a sense, a very painful thing in the entire history of Lattice Boltzmann, but maybe also a use, because as a scientist you always have to you need something to discuss. So there needs to be things that are unclear. Yeah, and this is one of these things where we spend a lot of time discussing, and I think we're probably not 100% at the end of this discussion. In particular, if you look in the book, somebody reading this book by Krüger on the Lattice Boltzmann methods, 2015. It was actually a time where a lot of discussion were on orthogonality, and this book is completely free of, this book is previously, so you can't learn anything about this, anything useful about this from this book. If you guys watch this, sorry, yeah. I think Tim Krüger will not watch my videos here. I think he already knows enough Lattice Boltzmann to not watch my video. Okay, the thing why we talk about orthogonality is that we like our different moments to be independent of each other. So independence in this mathematical sense means they carry different information. Yeah. So when you have one moment and you have another moment, you want them to have to carry different information. Otherwise, you have this redundancy, and this, first of all, you need to keep more memory than you would otherwise. And on the other hand, if you don't keep these two things consistent, then it may actually crash. Yeah, it's a big problem. So now, are the moments, if we define it that way, are they independent? Let's take an example. And the problem is in order to do this, we can now do this only for equilibrium, because today we just talk about the equilibrium. Yeah? But for non-equilibrium, this may be different. But let's look at the equilibrium. So suppose we look at this M200 moment in equilibrium. Then we have, of course, this integral over rho divided by 2 pi m kb kbt divided by, what do? I divide by m, sorry. And this is by 3/2 over xi times xi m 2kb t, and then we integrate this over not vector but xi square, right? We multiply this by xi square, so then we get the second moment in the x direction. And because I'm lazy, I've done this with Mathematica, and Mathematica gave me this. So the 2 pi goes away with the integral. Yeah, it's actually we have a 2 pi here, so that the integral gets the right value. Okay, so this is the second moment. And if we look 2 moments higher, so the fourth moment, so again, a lot of unnecessary writing. Minus xi times xi m divided by 2k Boltzmann t, and then goes with C to the fourth order, and we integrate this, and what comes out from Mathematica is 3 times K Boltzmann T divided by M, and we get the square of this and have this with the density rho. Okay, so what does this mean? So the second moment in equilibrium is related to the temperature. That we agree, we have seen this. Unfortunately, the fourth moment, even though it's not proportional to the temperature, but it's proportional to the temperature square, which means it carries the same information. Yeah? So these moments are not intrinsically independent of each other. Yeah? That's a problem. Yeah? So we get temperature squared not independent. Okay, so there is then an idea floating around in the sphere that you get independence through orthogonality. Okay, so these things are not independent of each other. What you know is Fourier modes, they are independent of each other. Why? Because they are orthogonal to each other, right? So what do we mean by orthogonality? And orthogonality is not necessarily the same thing as independence, but let's you know, this is the painful discussion that went on for many, many years. And orthogonality is not equal to independence, but let's see what we mean by orthogonality. Say we have a moment M, and this moment is, because it's a moment, it's an integral over a distribution multiplied with something. And we call this something phi, and because it gives us the moment M, we call it phi M. And this is given when we integrate over xi. And then suppose we have a different moment N that we get when we integrate f over a different phi n, but over the same space. So then we call this the moments M and N. We call them orthogonal with weight W, so this is now not the velocity, the weight W is a function of the velocity. Yeah? If the following holds, so if we have the integral from minus infinity to infinity, W xi into phi m and phi n. So phi m and phi n define the moments. And if we integrate this over the same space, and this gives 0, then the moments are called orthogonal with weight W. So one thing that is important here is that orthogonality can only define with a specific weight. I mean, what you can do if you don't know about this, you can assume that this weight is 1, and then you have your plane orthogonality, if you like. But this is only a special case of orthogonality. So what is the correct way of doing this orthogonality? By the way, this the first versions of the code used all completely unweighted orthogonality, and we'll later see why this causes problems. A little bit a better idea, but not necessarily the best one, is to use so-called Hermite moments. So Hermite moments take this kernel function here as Hermite polynomials, and the Hermite polynomials basically give us, they are defined from a Gaussian distribution, so they have the same shape as our equilibrium. That's the idea. Yeah? So, and here the idea is the orthogonality at equilibrium meaning that the weight function is the equilibrium. Now, you see, when, yeah, okay, let me just write this down. F EQ of x, now x is the independent variable that usually we call xi, but this is in general. So this is supposed to be proportional to an x squared divided by 2 sigma square, where sigma, not sigma square, sigma is the standard deviation, so sigma square is the variance. Standard derivation. Sorry, the standard deviation. Standard deviation. And x is our random variable. So a funny thing is that the random variable is the independent variable, yeah? Because it gives you the state this is occupied or not. Okay, so then the Hermite polynomials of various degrees I'm not sure Hermite is with E or without E. I think it's with E. Hermite polynomials of degree n would be phi n of x divided by sigma is minus 1 to the power of n e x squared divided by 2 phi 2 sigma square. I'm hoping that because I don't have this in my mind, I have to rely on my written text here. It is also, you will find different definitions of this depending on what you want to do. Because this exists with, with the definition of this sigma. So you have this with 2 sigma, and you will have it with just sigma, or 2 sigma square and just sigmas. So, but this is the definition we are using here. And if you apply this, now this I tested with Mathematica, so I hope it's true. Phi 0 would be 1, phi 1 would be x divided by sigma square, phi 2 would be x squared minus phi squared divided sigma squared divided by sigma by the power of 4, and phi 3 would be x cubed minus 3 sigma square x. I can't trust my own writing. Okay, it should be like this. And for the fourth one, it's 3 sigma by the power of 4 minus 6 sigma square x square plus x by the power of 4 divided by sigma to the power of 8. And because this is a Gaussian function and it's basically talking about the equilibrium, we have the same property as we have for the equilibrium, that multidimensional Hermite polynomials factor in their multiple dimensions. So we can easily write this for multidimensional Hermite polynomials because they factorize. So we can write phi NML of xi divided by sigma epsilon divided by sigma and zeta divided by sigma, so all the same sigma, would simply be phi n xi divided by sigma times phi m epsilon divided by sigma times phi L zeta divided by sigma. Okay, so this is possible here. So, and also we can define central Hermite polynomials. Central Hermite polynomials. These are, okay, I'll call them again with this fiddle here. Phi m, something is, okay. So they are very simple. That is xi minus u divided by sigma phi m of epsilon minus v divided by sigma and phi L zeta minus w divided by sigma. Okay, no big deal. Now let's see whether this at least does something and apply it to the problem that we just observed, that M400, yeah, we saw that this is not independent of M200. And now we have to define our variance, phi square, and the variance is of course this second order moment minus u square M00. M000. Now, to make things simpler, we now assume that u is equal to 0, and then we can say that this sigma square is k Boltzmann t divided by m is equal to M200 divided by M000. Now, our phi 400 is then 3m200 square divided by m000 square minus 6. Okay, I'm taking this one here, right? And I replace the sigma by M200. M200 square, nothing square here, M000, this into xi square plus xi4. So I'm replacing x by xi. And this is divided by sigma square, sigma to the fourth power, which is now this guy. Did I do everything correct? So, okay, so the thing is, we had here, I mean, this is sigma square, yeah, so then sigma square is m200, so this is because this is 4, power 4, this becomes power 2, and this becomes power 4, while it was power 8. And then our moment m400 with this fiddle on it is now the integral over this rho 2 pi k Boltzmann t divided by m to a third e by the power of xi times xi m divided by 2k Boltzmann t. Now this into 3m200 square by m000 minus 6m200 divided by m000, and this into xi square plus xi power of, I made a mistake, right? This is supposed to be 6, right? That's supposed to be 6. No, wait. No. Okay, no, 4. It was 4. You see, this is where I have my lectures usually in the morning. Xi by the power of, this is this xi by the power of 4, right? So m2000 divided by m0000 by the power of 4, and we integrate this over xi. Over xi. So now these things here are now what for the integral they are constants, right? While the other things here, they are not constants. They give us the moments that we want to see. So if we integrate over this here, because now this is a constant and it does not contain xi, what we get out is m. So this is wrong, right? So we get m000. Yeah, the zero moment, yeah, because we just integrate over constant and we have to multiply with this. So if we do this, then we get m for the first one, m00 times m2000, and I have something wrong in my script here, so I hope I'll get this correct now. The thing here, so what happens with this? This here is constant, but this here is not. Yeah? So when I integrate over this, what do I have? So internet, what do I have? Integrate. What moment gives this when I integrate this here with the equilibrium, this here? See whether you are actually following me all the time. Anybody considers this complicated? Is m20? Yes. So we get m. So we get 6 times m200. And we multiply this by m200 divided by m000. And up there is nothing with regard to m in front of it, but we have an m, we have a forced order, so we get m, m4000. And then we have to divide all of this by m200 divided by m000, and this to the power of 4. So what do we have then? Well, seems, okay, reminding us of the factorization, or we don't even need to use the factorization. We can also use this here. M200 divided by M002 is K Boltzmann T by M. You have a question? That is at the equilibrium. We're talking today, we're talking only equilibrium. Yeah? All of this is because you see, we integrate, we take the moment of the equilibrium. Yeah, so this is the equilibrium. So there's nothing else in here. Yeah. So now when we replace these guys to be certain, then we get 3 rho kb t by m square minus 6 rho kbt m square from this one plus 3 rho. So this is the one thing that we didn't like, tm square, and divided by something that we do not really care about a lot now anymore, because what we observe is that we have 3 times this minus 6 times this, which obviously gives 0. So why is this important? Well, yes, we are in equilibrium, but at least the equilibrium, yeah, of this first order moment does no longer depend on the temperature, which kind of gives us the hope that in equilibrium it will also not directly depend on temperature, in particular if out of equilibrium means just so out of equilibrium. Yeah? So that we are not very strongly out of equilibrium, but if we just have a kind of distorted equilibrium. Yeah? So there is close to equilibrium, there is no dependence of this Hermite moment, this Hermite first order moment on the second order moment and the temperature. So this is what came out here, and we'll see in future lectures whether this is enough or not. And this is actually this is definitely enough of a lecture for today.